This is the last video in my series on CART. So CART is classification and regression trees. If you're just tuning in, you probably want to go watch the other three videos before you watch this one. So I want to do two things in this video. I want to go over a very difficult function that illustrates the need to overgrow a tree and prune it backwards. Then I want to summarize everything that we've done on trees and when you should use a tree versus when you shouldn't use a tree. So the function that I have in mind is called the saddle function. So the saddle function is just, y is equal to x1 times x2. We've talked a little bit about this back when we discussed generalized additive models. This was an example of a function that was not additive. Okay, so it's not additive because we have a product of these two terms. What I probably did with you back in GAMs was if y is equal to x1, x2, and I take the partial derivative of y with respect to, say, x1. So how does y change when I change x1? The answer is it depends on the value of x2. Okay, so when x2 is positive, then x1 has an increasing relationship with y. When x2 is negative, you have a decreasing relationship with y. And when x2 is 0, there's no relationship between x1 and y. Okay, so the point is, this is a very complicated function because the effect of some x1 on y depends on the value of the other variable. And so that's an interaction. Now, let's think about how CART would handle this function. And what CART does is it tries to introduce a split on x1 or x2. So let's just say we were to split somewhere on x2. If I pick this value as the split, what's going to happen if I had a bunch of values following the surface? Well, the average of all the points on the left of that split would be 0, because notice the way the surface twists, half the values are going to be below 0, half the values are going to be above 0. They all average out to be 0. What would be the average to the right-hand side? Well, 0. And notice the overall average is 0. So there's no improvement if I were to introduce that split or any other split on either direction. So the point I'm trying to make here is the tree would never start to grow because there is no split that would improve the RSS at all. All right, so a method like CHADE that does a significance test and says, well, is the mean of the left child different than the mean of the right child, would never find a significant difference and it would never start to grow. So if you have a very complicated function like this, the smart thing to do is, well, just start introducing some splits. And as soon as we introduce one split, say right here, then immediately the next split is going to be able to carve off this part of the function, which would be very different than the rest of the function. All right? So the point is, one split doesn't get you anything, but two splits will start to find something interesting. So now this is it's a very difficult function to begin with, but you can't build a tree model unless you have two splits. There are no informative splits unless you have two. So this function really breaks trees and illustrates the need to overgrow the tree. Introduce some additional splits that maybe you don't need. But then we introduce a pruning phase to get rid of splits that we introduced when you don't have these nasty interactions to find. Okay, so that's very important to understand, and CART and C4.5 allow for pruning. So the implication is overgrow trees to detect such interactions, then prune unnecessary splits that you introduced. I have a your turn where I've created one of these complicated saddle functions where your x's are either zeros or ones. And so this is, I think, a very good exercise for you to see if you really understand how trees get built. And so what you're going to find with this is no single split gets you anywhere, but as soon as you introduce a split, then you'll find gold. So that second split will be very rich, and you'll see a very big improvement. You have the solution to that here as well. All right, let me just summarize the strengths and weaknesses of trees. So trees tend to be very fast compared to more advanced machine learning methods that we haven't covered yet, like neural networks. So trees are going to fit very quickly. Neural networks will take a long time to train. So I'm going to say that's a strength of a tree. Trees are very interpretable as long as your trees are small. And so we saw an example last time of this admissions example where we needed, what was it, 3 splits, and you could have a very interpretable solution where you can separate the admitted students from the denied students from the waitlist students. And so they're extremely interpretable, easy to explain to normal people, I would say, is another advantage. I can easily explain that admissions model to someone who hasn't studied machine learning before. Try explaining a logit to a normal person who probably doesn't remember their high school algebra, or not first year algebra. You don't get logs until this second or third course in algebra. Very hard to explain those things to normal people, where trees are very simple. I think another plus is the way it handles multi-level categorical variables. So I hinted at this earlier when we did the defaulting customer case, and that one had a predictor variable that was categorical. It was the payment status, and it took 4 different values. And the way trees handle that is they separate some values and push it to the right-hand side of the tree, other values to the left-hand side of the tree, and you've split your data set into 2 chunks in doing so. This is much more efficient than a regression model, where, let's say I wanted to include that same categorical variable where I would need 3 dummies. So I've got a base category plus 3 dummies, and I'd have to estimate basically 4 means to include that. It gets even worse if you have more values. So if you have the state of residence, that would have, say, 50 values. You'd need 49 dummies plus an intercept. With a tree, you would just start introducing binary splits, and you probably wouldn't need 50 splits to capture the effective state. A lot of these states would have the same effect on Y, and they would get thrown into the same node. So extremely good for multi-level categorical predictors. If I have a lot of those, trees would be one of the first methods I would turn to as a result. Trees are invariant to monotonic transformations of predictor variables. So what do I mean by that? Well, let's say I have some x. So here's my x and here's y. And if I wanted to make a split somewhere on that x, say x equals to 100, so all values to the right would be 1, all the values to the left would be 0, that's exactly the same thing. So x greater than 100 is the same as the square root of x greater than 10, which would be exactly the same thing as the log base 10 of x greater than 2. So all 3 of those cuts would be the same. It doesn't matter if I take any monotonic transformation of x, that split is the same. All the points that have x greater than 100 would also have the square root of x greater than 10, would also have the log of x base 10 greater than 2. So all of these are describing the same split. Nothing changes. So the point I'm trying to make with this is you don't need to find transformations of your x's ahead of time. We spent a lot of time doing that with linear regression. You don't need to do that with trees. Trees are unaffected by outlying x values, not outlying y values. A regression tree is going to be also sensitive to outliers, but at least not on the x side. Because let's say I had an extreme x that was way off on the next room in my house, well, it gets lumped into this bin and it doesn't exert a lot of influence. What happened in regression? Well, what we had in regression was, let's say you had a pretty strong positive relationship, and then you had one outlier. What we found was the regression line goes from something like that to something like that, and we would call that a point with high leverage. Okay, that trees cannot have that sort of influence because they just get lumped into a bin and the y get averaged. Now, again, if you have an extreme y value, means are not robust to an extreme value, but at least on the x side, you don't need to worry about outliers. Very well suited for modeling nonlinearities and interactions. That's what they're designed for. Very easy to score. So what I mean by score is if you have to take this model and apply it in, say, a relational database package that uses SQL. Well, you just need some if-then logic to compute the predicted values, and that's extremely easy. As opposed to something like a spline model. Try applying a spline in SQL. That would be very painful. Not well suited for modeling linear main effects. So what I mean by that is if your true function looks something like this. So here's x and here's y, and maybe my true relationship is that. Well, how do I represent a linear relationship with a tree? I'm going to have a whole lot of splits. So basically I need a step function to represent this, and I'm going to need a whole lot of steps, which means I'm going to burn a lot of degrees of freedom to represent that. So if you've got a nice, smooth, monotonic relationship like this, trees are not good. Linear regression is really good at capturing that. You need to spend 2 degrees of freedom to represent that relationship. You need a slope and an intercept, whereas a tree, you're going to need a lot to approximate that line. One thing that I often do is I'll fit a linear model or a GAM and pull out any smooth effects with the linear model. Then I'll take the residuals from that model and put that into a tree. So let's just have a quick example of this where maybe I have a situation like this. And let's say I wasn't smart enough to know that this was curved, and I threw my line in there. I would take the residuals and I would put that into a tree model. So basically I would say in R, tree, fit from my linear model. So fit, let me just write this out, fit equals LM y tilde x. So fit $residuals tilde x. You got to give the data frame names too. So I'm taking these residuals and I'm regressing it on an x. And if the tree starts to find some patterns that, hey, all these values in the middle have positive residuals, all these values out on the end have negative residuals, that's a signal to me that there's more to find. Now, it's not that interesting if you just have one x, but if you had 2 or 3 x's, this would be a way for you to uncover interactions. So if you're missing one of those interactions with the linear model, the tree would help you find it. Then you could go fit some product terms or something to really make sure you understand what that interaction is. A big negative of trees is that the prediction surface is not smooth. So you get these step functions. And then what we're also going to see is that trees are very high variance, unstable estimates. So what I mean by that is if you were to sample from your available data and fit a tree, then draw another sample from your data and fit another tree, chances are the splits would be a bit different. And once you have one split that's different from your previous tree, the rest of the tree ends up being very different. Okay, so That's a very undesirable property if you're interpreting these things, where the estimate is so dependent on the particular sample of data that you happen to have. I'll just point out that stepwise regression suffers from the same problem, where the first variable that comes into stepwise will change the model, the end model a lot. So if I bring in x1, then different variables come in versus had I brought in x2 first. Okay, so we don't like that feature. But what we're going to see in the next video is that this this is going to lend itself to ensemble methods that we'll be covering the rest of this week. All right, so that's it for trees. Let me just emphasize how much I love these. I love this method. It's one of the first tools that I'll use on a lot of problems for the reasons that I've just mentioned.